And this talk actually addresses the first of this picture. What we want to do at the end of the day is to fix the physics model, whatever it is. You can pick up your favorite one, and end up with collisions at the LHC. So we want to make all the connections from the Lagrangian to the events. And what this talk is about is exactly how to do that, how to write my Lagrangian on a piece of paper and get a computer code ready to simulate events. So that's the thing I will try to address here. Also, I would like, if you have questions during the talk, feel free to interrupt me. I really like that. So I really appreciate if you have a question, just interrupt me and ask a question, shoot the question. I'll be happy to answer. So the outline is as follows. So I start to briefly describe a kind of comprehensive approach for doing all those Monte Carlo simulations before moving forward with the principles behind implementation of models in the Monte Carlo tools. And by models, I mean any model you may dream of. There is no restriction here. You can think about something. If you can write a Lagrangian, we can input it into the tool chain. And at the end of the day, the talk, I will briefly discuss how to move from the models to the artifacting events, because this will be covered in the next lecture by Olivier deeply. I will just give you some appetizer there, and you'll have more in the next lecture. So let's maybe have a few words about what we want to do here. So my goal, personally, is to get more information on the path towards new physics. What is new physics? I still think there is some new physics somewhere, and I'm not the only one. And what I want to know at the end of the day is to get it from LHC data, try to understand what is the new Lagrangian, why should I replace the standard model Lagrangian? And there are several ways to do that, and the past is also there to emphasize that. So, for instance, if you remember a few years ago, there was some excess at 750, 100 GeV in a diphoton spectrum, the so-called 750 GeV excess. And what people did, they took their favorite Monte Carlo generator, leading order Monte Carlo generator, plugged many models and tried to fit and interpret the excess. And some of them were a bit more clever. They fit the model and tried to get some other signals that could be there and could help to characterize what's going on. And so what we learned from those 430 papers there, and we actually knew it before, is that Monte Carlo simulations play really a key role in the way to discover new physics. But there is more, because fitting excesses is one thing, it's a bit boring. Everyone try to do something. We may want to do to the next step and to really characterize new physics, get the final words of any potential new physics at the LHC. And for that, we need many excesses in different ways. And we also need accurate precision predictions. And by precision predictions, I mean predictions including analog QCD corrections matched with parton showers at least. And again, we can do that. So it's the same conclusion there. Monte Carlo simulations are everywhere. So we really need them, both at leading order to have a quick estimate of what's going on, and at NLO for having in mind what's going on further, try to see what new physics could be. So today, we can say that new physics is standard in the tools. Take your favorite tools, there are many models. Even if the model is not there, you can implement it easily. And that's the result of 25 years of work that started even before my time. And we can say that leading order simulations, that's a piece of cake. Everyone can just switch on the computer, plug a model, and 10 minutes later you have your answer. And the low QCD simulations, that can be done. It's a little bit more complicated. It takes a little bit more time. But within the MATGRAPH Seno framework, we can simulate any model and any process from any model somehow easily. And this is what you will see during this school. You will use the tools to try to do leading order simulations and also NLO simulations. And especially during the tutorials, you will really try that by yourself. So let's try to sketch all of this a little bit all together. So we start from an idea or a Lagrangian here. And what we want to do is to get the phenology out of it. And to connect this Lagrangian to the pheno, we have different steps. So first, we have this block that I called FEYNRULES UFO that consists in the model building part. We want to go from the Lagrangian to files written in some programming language that can be used by the tools. And if you want to do that at the NLO accuracy in QCD, you can use FEYNRULES, this new Moger package that allows you to play with the normalization of your theory, and then NLOCT to calculate the UV counter terms, and the other two components that are needed. I will come back to all these words a little bit later, so don't be afraid. I'm just flashing things there, but I will come back with more details later. And we get this kind of model library that is called the U4 NLO model that contains everything about your model. The particles, the interactions, what is needed for NLO calculations. Then when we are there, this information can be used by mathematics NLO to do predictions at leading order and next to leading order. And the code will draw Feynman diagrams, extract the matrix elements out of that. And then we can move to the next step, collider observables, by matching those matrix elements with parton showers. In the BSM case, we have to be careful, especially at NLO with all the resonances. If we have a rich spectrum, we can have, especially if we go to NLO, instead of producing the two states we're interested in, we can produce a third state that will decay into the state we're interested in. And those resonant contributions must be taken care of. And at the end of the day, we have collider events that we can analyze to get the pheno. So what we want to do with all those tools is to basically streamline the connection, as you can have guessed from the previous slide, from a Lagrangian. And a Lagrangian is something you can put on a t-shirt here. And if you don't like that Lagrangian, just change a t-shirt, there's no problem. And then from the t-shirt, we go to this, which is a CMS record of an event. And with a lot of tools, we can move from the Lagrangian simulating collisions, and with other tools, we can analyze those collisions to understand what's going on there. So why do we need several tools? Is basically what Fabio told you earlier. We have different processes occurring at different scales. And since we have different scales involved, we can factorize each block independently. And then we have one tool for the hard part, one tool for the softer part, and so on. So if we take this picture that you have seen already in the previous slide, we have our two protons colliding, and we have a very busy event ongoing there. So the first blob is this one, that's a hard process. And me, as someone who is interested in BSM technology, that's the block I'm interested in. Because if there is some new physics somewhere, and I still believe there is some, it has to happen here, in this blob, at the very center. And of course, for that reason, this blob is model dependent. It could be standard model, BSM. And you can use perturbative QCD to make calculations there. At the end of the day, so we produce some heavy particles, they decay here. And then we have a bunch of colored partons all around the place, gluons, quarks, and others. Those particles, I mean, they are accelerated color charges, they will radiate. And this is what we can call parton showering. So the color charge will radiate, the energy will go down, and so on. And we have a shower of partons there. And this is universal, that's bread and butter QCD. We know how it works, so we have tools that deal with that. As said in the last question, at the end of the day, all those partons will have a very low energy. They will hadronize and form hadrons here. And we also have some underlying events going there, something on the side with the random protons. And all of this is model-based. Some parts are universal, some parts are non-universal. And finally, all those hadrons that are there will interact with my detector and give this picture. And for this, we need the very low energetic interactions between hadrons and matter. So to summarize, we have the hard scattering at the TV scale, and this is maybe where new physics is. Then if you go down to lambda QCD, the QCD scale is basically the simulation of a QCD environment. And Leif will discuss that, I think, longly from tomorrow onwards. And we can even go further down to the sub-MeV scale, where we have the interactions with the detector. And I will briefly cover that in my lecture of tomorrow, but not too much. And I want to emphasize, at each step, we have a different set of tools that can be helpful. So this is a summary of all the activities that happened in the field of tool development for the last 20 years. So for what concerns matrix element generation, we have many codes. This is a small list, and I'm insisting there are others, just my personal choice for the main ones. We have new techniques to go to higher orders, both NLO and also NNLO now. We have parton showers, hadronization. We can match those matrix elements with parton showers. We can also merge if we focus on one final state, and we can simulate this final state plus one jet, this final state plus two jets, and then combine all of those things without having any double counting. And finally, we have a bunch of detector simulators on the market. So for what concerns the standard model, from my point of view, everything is under good control. All relevant LHC processes are known with a very good precision. We can expect even further improvements in the next few years. Could it be electroweak corrections, next to leading order corrections in QCD or even beyond? And Ambresh will discuss a little bit about standard model physics in the Higgs and top sector. So you will have more information on that later on, and not from me. So for new physics, the challenges are different. That's a map I like about new physics. It's been all the models, all the popular classes of models that are on the market, and we don't know where we are. I put the dot here, which is in the middle where there is nothing. That's actually very exciting. If new physics is there, we have no idea what it is, so we have to think. But we don't know where to go, because there's not any single side of new physics. All measurements, in particular the LHC, are standard model-like, so we have no leading candidate. There are many candidates, which means from the tool side, we need to implement many models in the tools. However, this may sound crazy, but today new physics is standard. All this complexity, take any model in that plane, we can implement it. And you have many talks during the school about new physics, dark matter, effective field theories, or BSM in general, by Kentaru, Ken, and Richard. Good. So, how to connect a tool? How to connect Lagrangian to tools? So that's the same plot as before, but I'm just drawing it in very different ways. So we start from the Lagrangian, and then we have a bunch of programs. FEYNRULES, Sarah, and LANHEP are the three existing programs that allows you to take a textbook expression and convert it into files. And the UFO is something in the middle that is, I will come back to it later on, that can be generated by any of these three programs, and that's just a rewriting of your model in Python. As I said, I will give more details later. From there, we can feed a matrix element generator that will itself can be matched with Spartan showers. We can add harmonization. We construct the events there, or even add some detector simulation on top of that, and we end up with our simulated collisions we can analyze. And as you can see there, we have tools for each step. So at this school, we won't study all of them, but those. So FEYNRULES and the UFO for the first part, MATLAB NLO for that part, PTR for the pattern showers and harmonization, and I will briefly mention Delphos and MATAnalysis 5 for the detector, the reconstruction, and the analysis tomorrow. So for now, let's forget about what's going on there, and let's focus on the first part, how to move from a Lagrangian to FEYNRULES and to the UFO, and how to implement models into those generators. So, how to do that? So first you need a t-shirt or a cup, works as well. And so I have an equation that contains all the physics. All the particles of my model are there, all the interactions, all the parameters, everything is in this equation. And this Lagrangian contains Feynman rules that basically explain me how all my particles will interact with each other, what they do, how they drink, how they dance, how they eat, etc. Everything is in that single equation. And I need to translate it into some programming languages. And if I want to do that for every model I'm interested in, and if I want to do that for every tool I need to use, I have to do the very same thing several times. It's boring, just extracting a Feynman rule, coding it. And if I take any simple model like the MSSM, where I have more than 1,000 interactions, the probability I make a mistake is, I can say 1. If you have to do one stupid thing 1,000 times, there's a good chance you will fail at some point, because it's just boring. At some point, you don't think anymore, you just do things, and that's how mistakes happen. However, this is systematic. So if it's systematic, we can use a computer to automate the full process. And this is where FEYNRULES comes into the game. We can systematize and automate the extraction of Feynman rules from a Lagrangian and their translation into some language that can be understood by a computer tool. So the FEYNRULES platform is not new. Today, actually, this is the 10th anniversary of FEYNRULES. I just noticed now. Well, plus minus some days, but yeah. So the first paper was from 2009. 10 years. Wow. So what FEYNRULES does in one line, takes a Lagrangian and gets some files in a programming language out of that. And it's automatic. What you have to do is to write your Lagrangian in Mathematica, and the rest is done automatically. There are very few limitations. Higher dimensional operators are all supported. Concerning spins, we can go up to 2 included. The basic color structures 1, 3, 6, and 8 are supported as well. So with that, you can do a lot of things already. And you can see the physicists as this caveman there trying to extract final rules for the tree. That's easy. We can do with the proper tool, but it takes some time. With finals, we more move to the industrial era, where you have this machine just take the entire trunk and destroy it and get all the final rules automatically, much faster. It relies in Mathematica, which is a very expensive package, unfortunately, but very useful. It's very flexible. You can do manipulations of all the symbols of the Lagrangian, even design new methods for own purposes if needed. Final rules itself contains many built-in methods if you want to do things in superspace, extract spectra, decay with, go to NLO, and so on. So it's a full toolbox where you can do a lot of things. And we can forget about those dark ages where we had to basically dig the things by ourselves. Things are automated now. And then from there, we can interface those blocks to many, many tools. For instance, CalCap, Finals, and Wizard have their own dedicated interfaces to finals. There were many more interfaces in the past. There are less and less now. I will explain why later. And we have the UFOs. And from a UFO, you can basically use many, many, many tools. Avic++, MATLAB 5, of course, Sherpa, Wizard, and more. So that's the strength of the UFO. With one single implementation, you can use many, many different tools. So that's a summary of what finals can do. So that's my model. I have particles, I have gauge symmetries dictating my interactions, parameters, and all of this is put into a Lagrangian. I'm feeding finals with that information, and finals can just extract the Feynman rules. That's the core function. But that's not all. We can go to one of these boxes below, get a dedicated interface to have a model file for CalCap, Finals, or Wizard, get a UFO so that you can use one of those tools, or just do extra calculations or theories we may be interested in. Do things in superspace, diagonalize the mass spectrum, investigate the decays, go to NLO, and so on. And if you're not happy with that, since it's Mathematica, you can design your own package here and add your name here with a new module. So what about all those interfaces I was mentioning? So what does an interface do in practice? It takes the entire set of vertices. It knows the tools that I will use afterwards, and you also know the limitations of that tool. So you can remove everything that is not compliant with the tool. For instance, if I want to use CalCap and I have a four scalar interactions and my scalars are colored, this will not work in CalCap. So what the CalCap interface will do is just to remove those vertices. And the same holds for Lorentz structures. If I have a higher dimensional operators, the tool I may use afterwards may not be suitable for that. In general, everything that is standard model-like or MSSM-like is supported, but if you have something different, you must be careful. The strength of MATLAB 5 is that everything is supported. There's no problem. You can go to higher dimensions, having crazy color structures, everything works. And then all those interfaces, what they are doing, they are translating this information into some language. So you can see that each interface is doing the very same thing. Again, we have a redundancy. And a redundancy is bad, because that means we'll do the same thing several times. And we have to maintain different blocks doing the same thing. That's where the UFO came into the game. The idea we have to have a UFO representation of the model that can rule all the interface out. And then the tools themselves that I will use there will take the UFO and just play with the UFO and remove what they don't need and keep what they can use. So we changed, the paradigm has been shifted. Instead of having finals itself cleaning what is useful for the tool and what is not, now it's the tool itself that takes everything and remove what is needed and what is not. And the good thing is that if at some point the tools is upgraded, it can do more, then we don't need to change anything at the finals level or at the model level. The information is already there. And that's much easier to maintain. We don't have to keep track of 10,000 tools to see how they evolve. Okay, maybe not 10,000. Let's say 10. So what is the UFO? The UFO stands for the Universal FEYNRULES Output. That's the name we decided in 2012. However, in the UFO2 paper that we hope to finalize this week, I said the same thing 1 year ago in FA. This name will be changed to the Universal Feynman Output because it becomes to be even more general than FEYNRULES itself. And it's universal in the sense that it's not tied to any code. The model information is there, period. And then if you want to use it, you can just deal with everything and just clean the stuff. So the UFO, in one word, is a set of Python files containing the entire model information. All the color structures, all the Lorentz structures, all the particles, all the parameters, everything is there. There is no restriction. So the model is just fully translated into Python. And it can also be employed for next tuning order calculations. So when we designed it 7 years ago, this was the model format for MatGraph. Now today, it's really a standard and is used by many tools on the market, probably because people thought it was a very nice idea to represent the models in that way.
So can you go back to mathematical also?
No. Actually,
It's not whole. I mean, the Lagrangian is not there.
the Lagrangian is not in the UFO. The Lagrangian is at the mathematical level, and then you have the Feynman rules, and this is translated. So you can in principle reconstruct the Lagrangian, but it's not easy, because also you have mass eigenstates, physical states in the UFO. Your Lagrangian, usually you use gauge eigenstates, and this information is completely lost. So there is no way to go back. You could think about ways to go back, but it's probably very complicated. I'm not even sure it's feasible, even in the standard model. So there you lose the information on the Lagrangian. That's why you can start to do something from the UFOs, but if you want to change something in the model, it's actually easier to change this at the Lagrangian level and regenerate a fresh UFO. So that's what a UFO model looks like. A set of Python files has a set, and the information is factorized again. We have the particles that are all in this file, particles.py, as you can guess from the name. The parameters are all in this file, parameters.py. We have a file with all the propagators for the internal particles. The vertices are split into 4 files. The generic one with the couplings, one with the Lorentz structures. And this I will not discuss, but you will discuss more in the tutorials. And finally, we have a bunch of files dedicated to NLO. So as you can see, the information is really well organized, and FEYNRULES does that organization for you. You don't have to write that file by themselves. It's automatic. You write a Lagrangian, and FEYNRULES produces all those files. So I will really not enter into deep details. The tutorials are there for that. But let's just have a quick look of what it looks like. So for particles and parameters, a particle or parameter is just a Python object with a name, like here that's a Gluino, GO. This is alpha S, this is GS, and attributes there. For the particles, we have everything about their representation, the spin, the color, the quantum numbers, mass, width, and so on. For parameters, we have their nature, if they are external, internal. In a model, you may have many parameters available, but some of them are not independent. For instance, alpha S and GS are good examples. We need both in the model, but once you fix alpha S, GS is fixed automatically. And the same holds for the electroweak sector. When you minimize your scalar potential, for instance, you put relationships between parameters. So some of the parameters are becoming dependent. And finally, we have a Lesuche-like structure to organize the parameters. Everything that is external can be spit out as a text file with blocks, and within a block you have different counters, so that you have all the Yukawa interaction in the same place, and you can change the value there. All the gauge sector is in another place. All the masses are grouped together, and so on. So please use during the tutorial time, don't hesitate to open those files and have a look to what they look like. So let's take now an example for a vertex, which is the main strategy behind the UFO, how to deal with those kinds of interactions. That's the standard model quartic gluon vertex. And the idea behind the UFO is to take that vertex and decompose it into a spin times color basis. If we check to this expression, That's the textbook expression. We have color structures here. So I have the structure constant of SU3 here. I have 3 tensors in the color space somehow. And those are what's going on with the Lorentz indices attached to all of those gluons. And again, I have 3 tensors in the Lorentz space. By decomposing this vertex into spin times color basis, I will actually write it like this. So this is my basis of color tensors. This is my basis of Lorentz tensors. And the coupling strength, the GS squared there, are my coordinates. And here I have only non-zero entries on the diagonal. For a given color tensor, I have a given Lorentz tensor. But in general, this matrix can be fully full. And there is nothing wrong about that. And the UFO uses this decomposition. And then we'll have we will input first information for those tensors, then information for the Lorentz structures, and finally the couplings will be the coordinates in that basis. And this is the strategy within the UFO. So now some words about NLO UFO, since a large fraction of the school is dedicated to NLO calculations. So that's an extending order cross section. I have the Born process with n final state particles. I have my loop contributions here with 1 extra particle running into the loop. So I have 1 extra integral there. And I have my real emission with 1 extra parton in the final state. Those two things are divergent, but the divergences are canceling each other. And they are both containing 1 extra power of alpha strong. If I want to do calculation with that, using my UFO model, this block here, the virtual corrections, requires me to add information in the UFO. So that MATLAB 5, EMC NLO, can do this calculation, can calculate that loop. And now I will explain why the UFO needed to be extended. But don't worry, if you don't get everything, there will be many lectures by Washeng a bit later this week, where we'll just address that in all the glory details. So in my case, I will just discuss the loop calculations. So that's a generic loop with a bunch of external particles, and that's how we can write it. We integrate over the loop momentum, we have a numerator, and we have a bunch of denominators associated with all the propagators that are going there. If I want to do this calculation, I will do it using dimensional vectorization, which means I will extend my number of dimensions from 4 to 4 minus 2 epsilon. That's a standard technique. And if I do that, the divergences will just be poles in epsilons, so that we can single them out. And then this loop is reduced to scalar integrals, where my numerator will just be 1, and then I will have some coefficients in front. And all this technique has to be done in d-dimensional space, where d is this 4 minus 2 epsilon. At the level of numerical code, that's a problem, because my computer can integrate in 3, 4, 5, 6 dimensions, but not in 4 minus 2 epsilon dimensions, because this is a real number. So the trick is just to say, okay, let's do the calculation in 4 dimensions and add the missing bits for this minus 2 epsilon dimensional parts. And those are the so-called R1 and R2 terms. So the R1 are originating from the denominators. The fact that I may use a 4D denominator instead of a DD denominator. And that's quite easy. It's super generic. We can replace them and add the extra bit automatically. And Olivier will discuss also that, the loop calculations. So the R1 are not a problem, because it's generic. We take a denominator and we play a little bit with it, and we get what we need. The problem is what we call R2 terms, and it's the numerator. And the problem with the numerator is that it's process dependent and model dependent. If I change a process, if I change a model, things are different. And if I use a 4D numerator, I will miss several components. And the thing that can be shown is that if my theory is normalizable, which is good if I want to do an NLO calculation, I can just use a special set of Feynman rules to calculate all the extra bits. And those are the so-called R2 Feynman rules. So if I want to do my loop calculation, I can just do it in 4 dimensions with the standard Feynman rules, and then takes my special Feynman rules and add the missing bits of the numerators. And this is what we call the R2 Feynman rules. They can be derived from the Lagrangian. And this is what a code called NLOCT that is shipped with Feynman rules is doing. It takes your tree level, your bare Lagrangian, and extract out of it all the R2 Feynman rules. And at the same time, the UV count terms are extracted as well. And this information is model dependent, which is why it has to be part of the UFO. So an LOCT will calculate all the analytical expressions that are needed for this, and then the UFO interface will just add a bunch of extra files that MatGraph can use to do loop calculations numerically in 4 dimensions. So that's the summary for the model part. So that's the same plot as before. And for now, I have covered what's going on here. How to go from the Lagrangian to the UFO. I didn't enter into any details. I just gave you the big picture. If you have questions, if you want to know more details, there will be more lectures later. The tutorial this afternoon will be on fine rules. I will be around. Just grab me, ask me further questions. I'm here for you, so don't hesitate. So now, in the last part of the talk, how much time do I have? 15? Wonderful. So I will start from this UFO and try to see how to link it to events. And again, I will not be fully specific because the next lecture will cover that into details. Please see that as an appetizer to the next lecture. And I will focus on problems specific to BSM, to new physics. So in this picture, I will now focus on this arrow, how to go from the UFO to the matrix element generator. And if you take this huge collision picture, now we are starting to treat this box here, the thing in the center, where new physics may hide. And what we have to do here, to do that calculation, we take the UFO, we fix a process, and then we need to generate all the Feynman diagrams and extract the matrix element after that. When we have the matrix element, we need to integrate it and generate events out of that. So for what concerns integration and event generation, I will not discuss that at all. I leave that for the next talk. I will focus on the first part. So that's the formula you have seen earlier today. That's the QCD factorization theorem telling us that the long distance physics here factorizes from the short distance physics there. Those are the parts on densities that connects how quarks and gluons can be part of the protons at a given energy. And that's my short distance physics component, the partonic cross section, where I can produce some new physics. And the fact that I can separate both regimes through a scale, this is why we call it the factorization theorem. This scale is arbitrary, which means I can vary it. And since there is no unique way to fix it, that basically tells us some information about the theoretical uncertainties inherent to my calculation. So I will focus now on this part, the partonic cross section. And we can use perturbative QCD to calculate it, and that becomes a series in alpha S. I'm just repeating what you have seen in the previous talk. And the more orders you include, the best it is. Until very recently, people could just focus on the first block for BSM. Now today, we can systematically calculate everything up to the second order. So NLO calculation for BSM, the problem is mostly done. I'm saying mostly, there are fine prints. So the idea now is to discuss how to get to Feynman diagrams from UFOs. So to focus on how to calculate this from a UFO. So if I take my Peskin and Schroeder book, I can read it, and this is how I will just calculate. That's, again, TT bar. This guy, TT bar, is very popular this morning. But this time I'm producing for a pair of quarks, and I want to draw to get the amplitude out of that. So I can just take my Feynman rules and apply them blindly. So I'll start with all the external particles. Those are fermions. I can use spinors. Those are the green stuff there. Then I have an internal propagator here. That's my gluon propagator. I put my Feynman rule for my propagator here in blue. And finally, I need to add my vertices. And I have two interactions. I will take my QCD Feynman rules involving the Dirac matrix here and the color matrix there, since the color interactions of the fermions involve both spins and color charges. So I have two gamma matrices here and two color matrices there, and GS squared. That's the coupling strength. And I'm done. So now if I want to get the squared matrix element, I need to calculate the conjugate amplitude. I will square it, and then I will do some algebraic calculations to get a better representation for the color non-structures. At the end, I will have to sum over the spin and color states and average for the initial state, and I'm ending up with this nice textbook expression. And I mean, Master 2 students, they can do that within an afternoon at our level. probably 10 minutes we can get there. It's easy, one diagram, 2-to-2 process. Of course, the life is more complicated. So before moving further, let me just say that this matrix element has to be integrated over the phase space. See the talk from Olivier for that. So that's easy. Life is actually more complicated because 2-to-2, one diagram, well, there's nothing really hard. The problem is that if I go to 2-to-n, where n is 3, 4, 5, 6, then the number of diagrams just explodes, and the complexity rises as n squared, which means that anything beyond 2-to-3 can be a real problem if I have to use a pen and a paper. Even 2-to-3, you can easily have 50 contributions to calculate, because each diagram has one amplitude, but then each diagram interfaces with any other diagram. So if you have 8 diagrams, you have 64 interference terms to calculate. So it starts really to be complicated. And we have a solution that is called Helicity amplitudes that allow us to reduce this complexity from n squared to n. The idea is to fix the external helicities so that this diagram for fixed helicity is actually one single complex number. And then I can just add all the amplitudes after each other to have one complex number and square it, and it's done. And I don't have to calculate all those interferences. So if we take a practical example, the same diagram, let's now do it in the formalism of the helicity amplitude. So we start with the external guys there, and I have two wave functions for a fixed helicity and fixed momentum. Then I want to merge them with this gluon propagator, and I will have the wave function of this gluon propagator that is basically proportional to this part of the amplitude. But again, for fixed momentum and fixed helicity. Then I have my final state particles there, and I will combine the wave function of these two final state particles with the one of my gluon propagator to get the full amplitude. And this is a complex number. So I don't need to play with matrix algebra and so on. And the building blocks of this diagram, we had actually 6 of them, are called Hellas functions in our language, where Hellas stands for helicity amplitude subroutine. That's a photon code that contains basically the full function. And for each Lorentz structure you have in your diagram, you have one Hellas code. They're of course not generic for any model. They were first designed for the standard model in the 91 by Kaoru. Then a bit later, they were extended to the MSSM in 2006. And then much further later, high dimensional operators were included, spin 2 physics, spin 3 half physics. So with all of this, it's probably sufficient for most models. But we even went one step further, and the ALOA package was released in 2012. 2012 was a big year. U4 and ALOA appeared. And what ALOA does, it takes your U4 and get the Hellas routine for any structure that is in the U4, and really any of them. So it generalizes everything. And on top of that, there's also one thing that's used in MathGraph, is that we can recycle information. If I have another UU bar diagram, I can just recycle this piece. I don't need to recalculate it a second time, which means I can just calculate everything that I need once, and I don't have to redo the same thing several times. So I can be more efficient. So let's plug some numbers there just to show you how things are getting easier. So if I have m diagrams, and if I want to calculate them analytically, I have to calculate m squared interferences. If I want to do it in the helicity amplitude formalism, I just need to do m calculation. So that's even better. And if I have to recycle, I still have m diagrams to calculate. Here I don't get anything. However, now let's take I have n particles. That's the multiplicity of my final state. So actually final state plus 2. So if I want to calculate everything analytically, it's n factorial squared. All possible combinations. In the helicity amplitude formalism is n factorial times 2 to the n. So it's better. And then if I'm starting to recycle, I can reduce the multiplicity by just moving n to minus 1. If you plug some numbers to have the order of magnitude, this is for an example for a 2 to 6 process. So you will not simulate 2 to 6 processes every day, but that's a kind of example at the border of what you can do on a computer, let's say a simple laptop or a small cluster. If I had to do things analytically, that means I have to calculate 1 billion of interferences. Impossible, at least with the pen and paper. If I go into the Helicity amplitude formalism, I divided that by 100. A bit better. And then if I start to recycle, the number is even divided further by 20. So things now can be, I mean, this sounds a large number, but for a computer, this is not so large. So with a good cluster, this can be done easily. So that allows us to really reduce things to a level manageable on computers. And that's why if we want to simulate even BSM at NLO, we can use simple laptops like that one. It's doable, because we are using a lot of techniques to make things more efficient. So the last topic I want to cover, which is very relevant for BSM physics, is what concerns decays. Usually, if I have a concrete BSM model, I have many states. So what could happen is that I will produce two new particles, like here, 2 gluinos. Then each gluino will decay into a squark and a standard model quark. My squark can decay here to a neutralino and another quark. My neutralino will decay to another neutralino, a Z boson, and my Z boson will further decay. And I have another story going on the second branch. So I will produce 2 particles, and then each particle will cascade decay into other particles. So we end up to a 2 to 10 process, a 2 to 8 process there. And as I said before, if you increase the number of final state particles, the situation becomes complicated, even with the efficient method. That's 2 to 8. Those numbers were for 2 to 6. So the question we can ask, do we really need to simulate 2 to n? And usually when people ask a question, the answer is no. And here the answer is no. And the reason is that although this may be possible, it's very demanding. We know that we have resonant contributions all over the place. So if I take a diagram with this final state and 0 particle in the middle, like a T-channel topology, for instance, it's clear that this diagram will contribute for nothing compared with the resonant one, which is this one. So we can just assume this and factorize the production from the decay. So here, I will simulate the 2 to 2 production of 2 gluinos. Then I will add the gluino decays into squark and jet, here and there. Then I will add the squark decay into a neutralino and another quark. I will add the neutralino decay here, the Z boson decay there, and I will just add things one after the other. So I will have one 2 to 2 process followed by many 1 to 2 decays. And by doing this, I can start to do things quite easily, even on a simple laptop. So how this factorization works in practice, so let's take an example where I produce a Z prime boson and a Z boson, and my Z prime boson decays into dark matter. It's a pity Richard is not there anymore, because now he has a Z prime. So if I want to write this matrix element, I will have the production of my resonance given by this current here, J1. I have my Z prime propagator in blue, and I have the decay of the resonance current that is given here. I can write my propagator as a sum over the polarization vectors. I can do this rewriting. And that's where the trick is. So I'm just replacing my propagator by this sum. And now I have a production matrix element here and a decay matrix element there. And I can calculate these 2 matrix elements separately. So there are then 2 ways to do it. And I will show that later. But before, if I do that, I'm of course losing on-shell effects because my propagator is becoming on-shell. However, if we start to vary the mass within the regime allowed by the width, we can partially recover most of the off-shell effects as shown in this paper. So there are 2 ways to do this sum. So that's my formula of before. And the first thing I can do is just to double this sum and consider the production completely independently of the decay. Yes?
Propagator is missing 1 over p square.
Yes, that's right. Yeah, there's a, thank you. The propagator, I have a 1 over p squared that factorizes. So let's assume it's included in the current. Sorry. So, so the first way I can do for doing this sum is just to separate in 2 sums. So I have my production here and my decay there, and then they are completely independent. And by doing so, I mean, this is not an equal sign here, it's an approximate sign. I'm losing all spin correlations. And that's something easy to be done. And that can give us some good estimate. If I don't care about spin correlations, that depends on the observables we can check. We must consider. It could be good enough. And this is what is done in Pythia, for instance. When Pythia handles the decay, this is exactly what Pythia does. However, we can do a bit better and keep track.
Narrow width approximation.
It is, because if the width is large, you cannot do that. Because then you need to consider if this guy here is white, we cannot do this factorization. We really need to consider the full process and potentially the interferences with the standard model. Okay, here there is no, because there is no dark matter in the standard model. But if we have a vector-like quark, for instance, decaying into a top quark in a W boson, then my vector-like quark production will interfere with the standard model. And if the width is large, this interference plays a key role.
For the Higgs, can you do this?
For the Higgs is narrow, or the standard model one. But if you have a heavy Higgs that is white, then you need to do the same thing. You need to, this relies on assumption that you can factorize the decay from the production, and the narrow width approximation is one of those assumptions. If the narrow width approximation is violated, you cannot do that at all. You can do it at the level of the code, but the result you will get are completely random numbers. So even if things are automated, that's a very important statement. All of this is completely automated. That means you will use those codes merely as black boxes. So it's good to keep in mind what you are actually doing, because the code may give you numbers, but the numbers may just have zero physical meanings. And that's up to you as a physicist to know what you're doing. And that's why it's good to attend those schools, because then you will know what you will do by using those tools. Thanks for the comment. So the second way is to keep track of the spin correlations and not to double this sum, just to keep the full thing. And then you can do it using reweighting as done in MathSpin that you will use, or more using spin density matrices like it's done in EPIC and Sherpa. So a last example, because I think I'm done with time now. So this is two examples illustrating the importance of the spin correlations. This is TTH at NLO QCD at the LHC, and that's the distribution of the cosine of the angle between the two leptons when the two top quarks are decaying into leptons. So I take the two leptons and I calculate the angle between the direction of the two leptons in the rest frame of the two tops. So I have one top decaying to one lepton. I can calculate the direction of the lepton in the rest frame of the top. I do the same thing with the TT bar, and then I'm calculating the angle between the two directions. And this is this distribution. If I just don't keep the spin correlations, so if I use this formula with the double sum, I'm getting this flat line here. Now if I do the full calculation keeping the spin correlations, which is the correct way to deal with it, I'm getting this black line. So this is normalized to 1. So don't look at the rate, but just look at the shapes, and you can see that spin correlations are crucial here. We are not even close to the good results. We are completely off. And this is a second example, more BSM-ish, where we produce two quarks. Each quarks decay into one way to produce standard model quarks and leptons and missing energy to neutralino state. And if I don't keep the spin correlations, I'm getting this distribution, the blue one, for the invariant mass of this down quark and this mu1 here. That's the invariant mass distribution of these two guys. So I sum their momenta and I square it. And I get the blue. And then if I keep the spin correlations that are important because I have a lot of fermions and vectors in the middle, I'm getting this red line. And actually, you can also do the full calculation. And this is the black line that you cannot see because it's exactly under the red line. So we have an excellent agreement there. So here, we'll have the shape more or less right, but we will be quite off anyways. So spin correlations are not always needed. It depends what you're doing. But if they are needed, they will change the results by a significant amount. So I think I'm fairly done. I tried to illustrate to you a little bit how we can link a Lagrangian to the pheno. Of course, I didn't cover the entire chain. It's impossible to do in 1 hour. I focus on this first 2 blocks and 2 arrows. And we have a complex process here. Going from there to here is super complex. However, we have different scales all over the place. So we can factorize the complex process into much simpler processes and then tackle each of them separately. So here, in that talk, I really focus on going from the Lagrangian you can write on a sheet of paper, on the blackboard, go to the Lagrangian to a UFO via FEYNRULES, and then from the UFO we can calculate helicity amplitudes and generate events. Event generation, that's the next lecture. Thank you.